Ladies and gentlemen, welcome to the Connect2Car Roundtable discussion entitled, What is the Benchmark and Expectation AI in Automotive? Your moderator is Michael Wagner from Edge Case Research, LLC. You are invited to submit questions for today's roundtable through the SAE International's WCX app. Ladies and gentlemen, Michael Wagner.
Hi, everybody. Thanks for coming out this morning. Appreciate your attention. We hope to have a very interesting conversation about a pretty broad topic for sure, and that is artificial intelligence, what its benchmarks are, what our expectations are as manufacturers, as users of the technology, and what we really hope to share with you are some of the key uses of artificial intelligence that maybe you're not currently thinking about. My background is in autonomous vehicles. I came out of Carnegie Mellon University, where I've been working on building autonomous vehicles for about 20 years. So when I think of artificial intelligence, I think of some of the technologies that enable things like automated driving. But I think you'll see, as we discuss today, that AI is used in a number of different settings, helping out the manufacturing process, helping out the software development process, and other things too. Of course, the role of AI in enabling autonomy itself is also important and critical. What my company, Edge Case Research, does is help validate the safety of autonomy technologies in a number of different ways, and we'll touch on some of those ideas too. We've heard in some of the sessions so far at this meeting about validation challenges and safety questions and different approaches to what you do with a system that is safety critical and that uses artificial intelligence. And this has been a question that I've been thinking about first at CMU and now at the company for almost 15 years now, it turns out. So certainly a lot of interesting discussion there. So with that, I'd like to hand it off, and we'll all be doing some introductions. And so we'll start with Skye.
Thank you. I'm Skye Matthews. I'm the CTO for the Watson Internet of Things business unit in IBM. So we're part of our sort of larger Watson AI division, specifically focused on IoT space, all things connected to the internet, including automobiles. My background is sort of a long time in systems engineering and embedded software development in a variety of industries, telecom, automotive, aerospace, defense, and so on. But more recently, looking at the connected things space overall. So, we come from a slightly different background. Obviously, we don't build vehicles. We're building some of the back-end systems that support connected vehicles, and of course, for many years now, investing in AI with Watson, building out our capabilities for supplying AI, both for enterprise systems, but increasingly for the Internet of Things space as well. Looking at how we use machine data and drive learning and insight from that machine data. So I'm very interested in this discussion, and I think certainly huge potential for AI in automotive in general, not just with autonomous vehicles, but all kinds of things surrounding our experience interacting with automobile systems.
Thank you. Good morning, everyone. Kai Stepper with Bosch. I'm responsible for automated driving and ADAS for Bosch in North America. My background is engineering as well. I've spent a number of different positions, both in automotive and non-automotive. Of course, Bosch is well known for the automotive presence, but as some of you may know, there's many different aspects on the non-automotive side, consumer goods, industrial technology. So I actually spent some time in industrial automation for a number of years. And when it comes to AI, Bosch is actually one of its own best customers in that sense, because we have worldwide more than 280 manufacturing plants that generate a lot of data in the manufacturing process. So you talk about data analytics, you talk about data mining, you talk about applying artificial intelligence to also non-automotive uses. We have spent a lot of time in-house actually tackling this problem. So I very much look forward to the panel discussion with all of you here this morning.
Good morning. I'm Bryan Goodman from Ford Motor Company. I'm in our data and analytics organization, and I lead teams applying AI and machine learning to a variety of business problems and engineering applications. It includes everything from Ford Credit, manufacturing, safety, business domains such as even human resources and legal, but also a lot in even our product development engineering space.
Hi everyone, I'm Chetan Merista. I'm the CEO and co-founder of Locomation. Locomation is building autonomous driving technologies for semi-trucks. And most recently, before Locomation, I was a special faculty member at the Robotics Institute of Carnegie Mellon, just like Michael. I've been in robotics and AI for about a decade now, so I've got great exposure to all elements of intelligent robotics and autonomous vehicles, with a little bit of specialization in machine learning and mostly in perception.
And I'm Allison Malick. I'm the Chief Operating Officer of May Mobility. With May Mobility, we focus on providing self-driving transportation focused on the enterprise use case for low-speed first mile, last mile. And part of that is really focusing on what technology can actually do today. So instead of trying to look 10 years out and cross our fingers that some really big R&D challenges can get solved, we decided to reduce the state space that we had to design for. And we'll expand that over time as new sensors and new breakthroughs happen in AI. And so for us, a focus is really on making sure that AI earns its place at the table. I come at this from a background of automotive engineering. I actually worked at GM for 6 years as an engineer in electrification, so learned what it meant to be a release engineer on a brand new part that we'd never figured out how to launch before, and then moved into corporate venture where I was looking at applications of AI across the enterprise. So looking at manufacturing opportunities, looking at natural language opportunities that would help with the speech recognition systems, as well as opportunities in autonomous technologies.
Hi folks, my name is Jack Wiest. I'm a Senior Principal Engineer and Vice President of Automated Vehicle Standards at Intel and Mobileye. And we are in the business of trying to figure out how to deliver safe products that use a lot of artificial intelligence. So we have some firsthand experience there and continue to do research on this challenge of how do you validate, verify, and ensure a system that uses AI is safe for all of us to be passengers in an automated vehicle. So, thanks.
Thanks, everyone. Yeah, so I guess maybe let's start the discussion by doing a breadth-first search of some of the different things that we might want to talk about here. Again, I think that people think about automotive, they think about autonomy in charge of actually driving, but there's obviously huge supply chains, a lot of technologies that go into that. Maybe you can give a specific example of a way that AI has enabled some kind of new sort of product development capability that we're not as quite aware of. Skye, do you want to start?
Sure. We've certainly got several use cases in flight now with applying AI in different aspects of automotive. So I'll pick some on the manufacturing side. For example, we're starting to apply vision, machine learning, and image recognition to the manufacturing process. So instead of having to sort of manually inspect every weld or the paint job, we can actually use cameras and image recognition to do that inspection, speed it up significantly, correlate it with other machine data so that, for example, if we see a paint flaw, we can classify that and correlate that with other readings coming from the paint systems or HVAC systems, et cetera, that might tell us exactly why this paint flaw is showing up and how to correct it really quickly before it starts affecting a large run of production. Very expensive to correct paint after the fact. So that's one example. Another one in sort of operations is the use of acoustic data, and this one's quite interesting to me because we get a lot of sensor data, but as humans, we often sort of diagnose things by ear, right? Mm-hmm. If you're an experienced technician, you know that the whump, whump, whump sound means something on this particular vehicle, and it sort of helps you diagnose it. Well, we can use machine learning on acoustic data to do sort of similar pattern recognition and diagnosis on acoustic data, working with a couple of manufacturers already to start testing that just using sort of simple acoustic pattern recognition to diagnose some early prevention and maintenance for vehicles on the road. So both sort of interesting ways to improve the sort of end user satisfaction, better quality product, as well as more easy maintenance and less sort of downtime waiting for something to break, right? We get it into the shop, diagnose, fix, get it back on the road much faster.
Sure, I mean, just to respond to that a little bit, we had, there was an interesting early project at Carnegie Mellon that was looking at maintenance of belts carrying coal out of a mine, and there's a lot of the same kind of value proposition there, so. Kai, would you like to?
Since Guy brought two examples, I will bring two examples as well. One automotive and one non-automotive. So my first one is from the manufacturing side as well. I alluded a little bit to, let's say, the size of our manufacturing footprint worldwide. And one of the, let's say, topics that you have when you want to deploy artificial intelligence is data generation. And in the manufacturing world, from the Bosch side, we don't have a data generation problem at all. You can imagine 280 manufacturing sites worldwide, they create plenty of data. And one particular aspect that we have looked at is, of course, the aspect of preventive machine maintenance, but when we manufacture the product more specifically, is the classification of not only if the finished good is good or bad, but when it's not good, what exactly is wrong with the part, which, for decades and decades, different methods have been deployed, electrical, acceleration, noise and vibration measures, but to deploy artificial intelligence and really the classification aspect of what exactly is wrong with this part. Is it a bearing, is it a shaft, is it a cracked housing, what have you not, where we have successfully deployed artificial intelligence in that context. The other one I think is probably more widely known in the automotive context. One of my responsibilities is automated driving here in North America. So when artificial intelligence has specifically shown its strengths in terms of solving classification problems. Very widely known from image processing, things like semantic segmentation are well known, but if you now multiply that with multiple sensor inputs, not just image data, or video stream, but also radar data, LiDAR data, different sensing modalities, and now make a certain classification decision that then helps us very greatly in the behavior generation aspect that follows as a step. We have successfully deployed artificial intelligence in that context as well.
Thanks.
Great. Yeah, I'll try to give two different examples. One of those is in engineering space. We've trained AI systems to approximate the physics models that would normally be accomplished through, say, finite element analysis for something like optimizing a part like a wheel and determining stresses on that wheel and different material thicknesses that are required and those sorts of decisions. And by training an AI system to approximate it, we can run those analyses much faster. 1 or 2 orders of magnitude faster, which then allows a much faster iteration cycle for design, many more opportunities to try different things and end up with a better design. That's one space. Another is in natural language understanding, a field that's really advanced tremendously over the last roughly year even. And looking at different data sources, we also have significant amounts of data, especially in text, about the performance of our products out in the field. Things like, say, warranty claims and other customer feedback and technician feedback. And applying natural language understanding to that has allowed us to really step up the game even further in ways that we're able to get feedback and detect both potential issues, but also opportunities, and get those to the right engineers even faster than before.
Yeah. Chetan, do you want to? Now we'll go to the vehicle guys.
No more examples left for me. I'll make something up now. Let me make 2 comments. First is when we say AI, we usually mean a very vague concept. So these days, everything is called AI. And if you actually try to look a little bit more into that, AI is always this abstract thing that we still couldn't figure out how to do yet. It's always the pink unicorn under the rainbow. As soon as we figure out how to do something, it assumes a more technical and less sexy name like support vector machine and just becomes a part of our daily lives. So if you look at it with that perspective, AI is actually everywhere. AI sets the temperature at your house. AI sets the cruising speed in your cruise control. AI does everything. So it's really ubiquitous by now. The second point is, let me try to give a more specific example of AI going forward is, as Allison said, the overall automation, at least in the AV context, is many years away, if not decade or decades away. And we decided not to wait for that eventual very rosy future, and we started with select regions, select applications, select use cases to conquer first. And pretty much like that being a progression, that being an incremental process, the overall who does the job, who makes the decisions, is it AI or is it human? It's also not a binary thing. So there are use cases going forward in the near future where AI assists or guides or guards human decision making, or vice versa. And that actually poses a very interesting problem. Again, in our previous life at Carnegie Mellon, we've done some very interesting projects investigating how AI and human decision making can interplay in the context of autonomy especially. And the main problem there is, well, when we say AI, we mean that vague thing, but under the hood, it's all numbers, and it's all matrices, and it's all equations, and computers are inherently very good at that. They can crunch billions of numbers a second with no problem, but for AI and humans to do this interplay properly, they need to have a shared mental model. They need to have a common agreement on what it means to do X, Y, or Z. And that turned out to be really, really challenging. So how to get AI to distill all these numbers, millions of numbers, and present it to the human on time and without desensitizing the human's decision-making capabilities is a very interesting problem. And that itself includes, it's in a very Inception-esque way, that itself includes another application of AI, how to do the semantic interpretation of large amounts of data. So going forward, I see that as still an open scientific challenge and a very, very important feature to have, so that if we can get AI and people to speak the same language or understand the same symbols, we can conquer more of these spatial use cases before we get to this more rosy future.
So with the work that we do at May Mobility, I hinted at where I'm going to go with this, but we make sure that AI earns its place on the car. And that goes back to some of these ideas around validation and reliability, which we may touch on today. I know got touched on a panel yesterday. But with that, it means that we're really focused about where can it add value today or in the future. And when we think about AVs, part of it is getting it to work. And getting it to work everywhere all the time and at all speeds is going to take a while. Getting it to work at lower speeds and specified road networks and things is a much more tractable problem, and that's what we're doing. But just because the car works doesn't mean people are going to use it. And at the end of the day, even if all of us are extremely successful in creating self-driving vehicles, if we make them in a way that people don't want to use or are afraid of, we will not be able to have the impact that we're all hoping to. And so one of our other focuses, because we're out, like people can ride in our cars, the general public can ride in our cars in Columbus, Ohio, they can ride soon in Providence, Rhode Island, we've got vehicles out here in Detroit, we've got people, we're learning, and people have a lot of questions. They want to understand how the car works. Maybe they get car sick, so they want to be able to ask the car to slow down. Those types of things, and so what we're seeing is a great opportunity for AI in the natural language space, to be able to create a comfortable dialogue where we're not asking people to learn 5 new hand gestures or 6 new phrases that they have to say every time they get in our vehicle to be able to interact. We want them to be able to react however they need to, and for us to understand that information and create a great ride for them. We think that's really key for making sure that the promise truly comes to be. The other way that we use AI is actually off-board the vehicle. Our behavioral planning is a bit different, and so I'm not going to go too deep into it, but if you look up multi-policy decision making, there are papers, so have at it. And with multi-policy decision making, we actually establish policies, which are little, essentially vehicle controllers that help the vehicle do very simple types of tasks. And actually establishing those policies, we see opportunity to use AI to help us better understand from all of the driving set of data, what is the least number of policies that we would need to develop in order to drive safely, and then we can actually use AI to help us develop those policies, and that allows us to advance our system more quickly, but also because it's off-board and sort of before, software development before launch, lets us take that time to make sure that we're getting the robustness that we need in the output of the AI.
I think Allison said something really interesting about this trust challenge that we have, right, with consumers who are using these products on a daily basis. I mean, if you think about trust, if you were to look up the definition, it's a human emotion, that's based on open dialogue and communication and feelings of being validated by the person you're talking to. So trust is something that's established between two humans. So how do you establish a human emotion between a human and a machine? And artificial intelligence to most kind of lay people sounds scary. They think of Skynet and things like this. And so part of our challenge, I think, is not only to understand how to use AI responsibly in a safe manner, and that's what we've been working on at Intel and Mobileye. The keynote earlier this morning talked about a technology that we've released to the industry called responsibility sensitive safety, which uses sort of old school AI, which is a formal model that's rules based, to protect against possible mistakes from modern artificial intelligence techniques. And so we think transparency and openness, to not only the industry but also our customers about why is the automated vehicle doing what it's doing? What did it see? Why did it do what and when? Not only in accident scenarios, but just in everyday drive scenarios, is going to be a really valuable asset to help establish and build that trust relationship inside the vehicle for the passengers, most of which are not going to be technically inclined and understand the technology behind the scenes. So I think as an industry, I think we do well to remember the human element and how that human trust relationship is an important a goal for us as we deploy artificial intelligence.
And I think one thing that we've seen in common here is actually that humans are of course using all of this automation in very different ways. Just as a designer needs to have trust in the optimization that gets spit out by a CAD tool, the rider also has to have trust in the control system that they're driving around Detroit in. So it's interesting to think about what kind of benchmarks we have for that trust, right? Mm-hmm. So how can we know that that AI is sort of moving things in the right direction? Maybe you have some experience with this, having deployed it early. And I think this is a critical thing to track, because we need to be able to not just talk about hype and what might happen if we have general artificial intelligence in the future, but really how we're tracking progress through some of these early kind of products. So do you want to speak a little bit about what those early benchmarks, those trackable kind of things, especially when it comes to humans trusting these systems?
Yeah, that's a good question, and I think it actually has to start with the engineers, the people who are closest to the technology. In a lot of cases, there's two issues that we succumb to today. One is, as sort of Jack referred to, we don't really know how, particularly some of the deep learning stuff actually works. And so it's very hard to get transparency into why it made a particular decision, or why did it classify something a particular way. So we certainly have to get better at that. As engineers, we need the tools, as well as the depth of understanding, so that we can actually explain how our systems are working to ourselves first.
So we're supposed to have a conversation, so I'll take us off.
Yeah,
do we actually think that's possible? Right?
So that's a great, there's a lot of debate about that in the community right now.
Yeah.
I personally believe it is.
Okay.
And we in IBM are certainly working on some tools to help with that. I don't believe it's an intractable problem, but it's a difficult problem, no doubt.
It's almost like an aspect of self-discipline, though. Like sports cars can go hundreds of miles an hour, but when we're on the highway, we follow the rules because we've established that for people's safety, and we as an industry are trying to answer to an evolution of technology that has taken place very heavily in consumer, where it's okay to be 99% good.
Yeah.
It's not okay to be 99% good in automotive. And so I'm actually really excited about the discussion moving towards explainable AI, because when you're working in an industry where people's lives are on the line, it's not a question of if. It's a question of must. And even if it's a situation where you're not taking your sports car at 200 miles an hour, because 70 is what is safe for everybody, that's really how we need to think about it when we look in the automotive space. If you think of some of the other examples that give me pause, are a lot of the sort of image recognition systems. They're as good as you train them to be. So a lot of image recognition systems are not good at looking at people of color, at women, at elderly people, and being able to discern those images because they're not trained on them.
Right.
And so it actually does come back as well to the engineers really thinking about and understanding the implications of their system.
Well, this is why the metrics that you're trying to track are so important, right? And I think sometimes even defining those is part of the challenge, because if we knew a set of rules that we could encode into a system to be able to optimize that design, to be able to detect those pedestrians, we probably would not have used machine learning in the first place, right? Because it would have been old-fashioned AI, like you said, Jack. So I guess I'll raise my voice at the end of that sentence and make it a question.
Yeah, I think I'll add. I think part of the challenge as well is what is the metric?
Yeah.
You know, and particularly in the automotive space, where especially in the U.S., we have sort of a self-certification sort of model. You know, I can claim I've achieved some metric, but my method of measuring it and my evidence to support it could be totally different than a peer company. You know, so how are regulators or consumers able to make an apples-to-apples sort of comparison? You know, there are metrics out there like miles driven, for example, being, of course, the most famous one, and I could drive 1 trillion miles on a street with no other cars, no stop signs, no pedestrians, no traffic lights, no nothing. Doesn't mean it's a safe car, but my metric says I've driven more than everybody else, right? So you could also say I should be statistically better than a human. Well, and as you've probably heard, well, what human? The best human driver? Because the best human driver is actually quite a good driver.
Right.
Maybe in their lifetime they've never had an accident. Or the worst human driver.
And
drunk
we're all
human
the
driver.
best human drivers.
Yeah, we're all
up
the
here,
best.
by the
It's
way.
the other people that are the
yeah,
problem,
these
right?
guys, whatever.
So, so I think that's part of the challenge, right? Is gaining consensus on what metric, what is the metric, but not only definition of the metric, but then how you assess the metric also needs to be common as well.
So, go ahead, Chad.
Yeah.
In some sense, we have the same metric problem when industry is choosing human drivers as well. So I'm in the trucking industry now, so I get to learn how trucking companies, how fleets are basically operating, thinking, what they are looking into, because they are operating at such a large scale that they are even more obsessive than my former self, for instance. I would have never thought of some things that they have been very, very obsessive about. So when they are choosing their drivers, they are looking at a different set of metrics. It's not just the miles driven. Yeah. So there are long haul drivers with 2-3 million miles under their belt, but they've done very little city driving. So most of their miles were dumb. They were just behind the steering wheel and not doing anything literally for 500 miles, and they spent 20 years like that.
Yeah.
Wow.
So I've heard some people claiming that you have to look for like a mixture of long-haul driving because it has some endurance problems, some different experiences, different weather maybe, and in-city driving because that's when you get all this uncertainty, and that's when you get all the Pittsburgh left guys that are coming from all the way to the right, all the way to the left in 10 meters.
And you need to model them when they're each trying to tell you to
exactly.
go, and then you have a deadlock.
Exactly.
Yeah, right.
So finding the right metric or set of metrics is definitely the key. But maybe we don't have to invent something completely from scratch. Maybe we can still tap into some industry experiences somewhere in again, particular use cases.
So I just want to take it back to Bryan and Kai a little bit because if we look at different applications of AI, and of course I love to think about all the things we just talked about, but there's a ton of AI being used, and maybe there are a lot of really useful lessons in terms of how you track it, because you're not tracking just the number of parts designed. That's not, I've designed 1 trillion parts, and so it's good. Like there's certainly a lot more fine-grained and meaningful things, and maybe we'll switch up the order and start with Bryan.
Sure. Yep. Yeah, I think AI will likely always have a perception problem about being, say, a black box.
Right, right.
Because it certainly can be used that way.
Yep.
But if you have to work a little harder at it to be able to make it explainable AI, but it's always possible in my experience. I think I cannot think of a single example where we have not been able to dive under the covers in the in AI models and explain why it's doing what it's doing and figure it out. And it does take significant work as the models get very complex, but it's always been possible. One quick example that I had was we were working with our Ford Performance racing team on a computer vision application. And
it's a good follow-up, Allison saying you can drive super fast.
Yeah.
Let's talk about racing.
Wait, if you're on a track, you're good.
Yeah, that's
Yes.
right.
Those pesky pedestrians.
Sorry, go ahead.
And obviously they did not just want a black box. They wanted to have a lot of confidence in this, right? The cars are going 190 miles an hour. And we were able to really probe the model extensively and show very convincingly that it was doing exactly what they wanted it to do. It did have some surprises, but we were able to figure out exactly what it was doing and why it was doing that, and it turned out they were actually good surprises. The AI system picked up on visual cues such as the difference in the shape of the grille between different NASCAR cars. The NASCAR cars often change their color scheme and sponsors every week, but the grille stays the same, that one driver races for the same manufacturer all season. So the AI system picked that up. Humans hadn't necessarily thought of that ahead of time, but it was very easy to figure out why it was doing what it was doing.
So maybe to add to this, Bryan, and to your question, Michael, I mean, this topic goes right back to the core. What is artificial intelligence in the first place? You know, the way we have to find it as humans is to simulate intelligent behavior. Intelligent behavior of whom? The only benchmark that we have right now is human beings. So we try to imitate human behavior and human intelligence. And that's where it gets really, really tricky if you want to, let's say, apply a certain benchmark or a certain metric that you have learned or have come to accept, let's say, in a non-automotive application versus an automotive application. So it's one thing if you have a certain performance indicator. So if I don't have a full 100% performance when I classify my finished goods at the end of the production line, maybe that's not the end of the world, because with the multiple inputs that I have, I most likely have already exceeded what a human would have been capable of to say, hey, here's a cracked housing, or actually you have some bearing fault that a human being from the outside, just by visual inspection and noise inspection, wouldn't even be able to classify. Or maybe it's okay if your speech recognition AI doesn't perform 100% of the time. Yeah, it gets annoying if you keep talking to your infotainment system in your vehicle and it doesn't pick up, and I'm sure we have all been there, but it's not the end of the world. But that's where we need to differentiate between performance tasks and safety critical tasks.
Yes.
Two very different things. So when it comes to speech performance or classification performance, that's one thing. And you can even put it in an automotive context. Let's say, okay, if you don't really have 100% traffic sign recognition performance, maybe that's not the end of the world. Sure, speed signs, for example, are safety critical, but it's very, very different than making a decision if you should enter the intersection or not in a certain given scenario. And that's why, unfortunately, in our experience, metrics, performance indications that you have from non-automotive applications like natural speech recognition, for example, manufacturing world, don't translate, unfortunately, that easily to safety critical automotive tasks. And that's where it gets very difficult.
Yeah, I feel like typically, we measure the performance of these systems against, their performance on a validation data set, and we look at the overall accuracy across that whole data set. I think that's a mathematical way of framing exactly what you're talking about.
Exactly.
It's also the way that we like to think about the problem that Allison brought up, which is that there are sometimes sub-problems within the problem, and your performance on those sub-problems also has to be good enough, right?
Yes.
And so, at the risk of getting a little bit too technical, I'm very curious, since we have all of you up here, about some of the processes that you've tried to adapt to try to solve those kind of problems. I mean, we talked a little bit about some of the reverse engineering that needs to go in, the failure diagnosis that needs to go in. Those processes become part of your overall engineering process with AI? Is that how it's being adapted? And I guess we'll start with the autonomous mobility side of things here. I mean, in terms of like expanding ODDs and understanding what these pieces are, this part of the process really feels like a core thing to what May's doing.
Yeah, so with what we're doing and what I talked about with policies, right now we're operating with 3 policies, which is pretty low, but actually works really well for urban environments. There's a stop and go and a slow down.
Mm-hmm.
You don't really usually want to drive aggressively, but
Very
we're
explainable.
looking at some other cities, and those are handwritten right now, so they are. You can read the code and understand what's going on, and now we're using all of the rich data that we've been able to get from all of our driving in Detroit, all of our driving in Columbus, the driving that we've done in other cities, to be able to then understand, okay, which situations could have been smoother. So for us, it's not an issue of can we do the thing? It's can we do it well? Can we do it in a way that makes the rider feel comfortable so we're not slamming on the brakes? And can we do it in a way that makes the other drivers understand what we're doing? And we're actually really proud of the fact that our vehicles don't slam on their brakes. They're actually very natural in how they negotiate with pedestrians at 4-way intersections. We can slow down and let the pedestrian pass. And that's really comes back to this idea of how MPDM works. As we get into more complex scenarios, we're looking at which features we should start to unlock. We can then use AI to help develop those features and then dig in to see what are the insights that came out of that so we can explain it. Because at the end of the day, nothing's going to go onto our car and into the public if it's not something that we can explain.
I think one thing that we do in our design philosophy at Intel and Mobilize is, and Allison kind of mentioned something earlier about just because your car can drive 180 miles doesn't mean you should. And so is the same true for us when we consider when and where should we be using AI. Because just because you can doesn't mean you should, because there's other factors, partly the explainability piece, the ability to formally verify, but also the cost. Particularly for consumer vehicles, there's some amazing technology in there for what we pay. But if we used a big, huge end-to-end AI algorithm that would add thousands of dollars of cost to every vehicle because you need a 500 teraops machine to run the code, then we're not delivering safety value to to all of society. It might be available only in really high-end custom vehicles or something. So part of it also has to be the deployment cost, and so sometimes there are simpler techniques that can accomplish the same goal. Classical computer vision algorithms, for example, are very good for identifying certain kinds of things. And so yeah, you could train a model to do it, but if you don't have to, your system often can be more efficient, lower computation requirements, lower cost, and so then wider availability of safety technologies. So I think as excited as we often are, and I'll admit that students that we get out of CMU and other great schools like that, they come out with this mindset that I've got this one hammer and it's the best hammer that's ever been created.
I mean,
and I want to use it everywhere.
Exactly.
It is the best hammer though. And so I think we have to caution ourselves sometimes as engineers and reflect just because it's cool to do something doesn't mean that we should.
Yeah.
Because there are other factors involved in the design.
Yeah.
I'm going to say something very, very similar. So let me do the shameless plug part first and explain in 30 seconds what we are actually doing. So at Locomation, we are, as our first step towards this fully autonomous future, we are actually doing autonomous convoying, in which we bundle 2 trucks together and we remove the driver from the follower truck. So the follower truck is a proper level 4 fully autonomous truck, but it's only level 4 for this extremely limited ODD. Its only job is to actually follow the leader. And that basically enables us to do it in a non-machine learning way. So we have machine learning based perception systems that we are validating and that we are keeping an eye on, but they are not on the safety critical path. And since we were able to distill down the problem, dumb it down to that extent, we actually were able to use some of this old-fashioned, now look down on old computer vision, geometric computer vision methods that are actually explainable. You can go and you can read the code, you can check the formulas, and you can basically validate them against your spec. And that way, we are actually able to demonstrate full autonomy, but only for this very, very small niche use case that just happens to be around $100 billion a year market.
It's funny how that works.
It's funny how that works.
Wow, this is solvable, and there is a market. Back to your point, figuring out, as exciting as it is as an engineer, of like, we could do everything. When we think about impact, you have to make sure that like it can meet people, and thinking about cost is an important part of that.
Yep. So we're getting a couple questions about sort of the public's perspective, and I want to pick up on this idea because I think the hammer of deep learning or whatever it is actually like a beautiful vision, right? And not just for those of us that have a lot of academic experience. I think that idea gets out into the public. It also, I think, legitimately helps us all first build systems that can be shown to be doing things. So can we maybe, as a public service announcement, give some useful examples from our own experience about how just showing that you can do something, it doesn't mean that you can always do it, or that you actually have a super reliable product, because I think that is, to me, maybe this is something you can refute. It seems to me that this is a key aspect of machine learning, is because it allows you to synthesize a design really, really quickly. But a point that I want to make to the crowd is that you're hearing all the like back-end work that's required once you get that design, and I think that's maybe that's a piece of the answer to my own question. Sorry, Skye, do you want to start?
So I'll go back to some of the conversational system work that's gone on, because that is an area where we can do some exploration without it being safety critical, right? We don't have to be 100% accurate. Well, in fact, the first systems that were out were not good at all, right? So, we've certainly gone on a significant journey. In the early conversational systems or voice control systems were not based on deep learning or AI models at all. They were more traditional statistical models of speech recognition. And then as that evolved to AI-based speech recognition, okay, the sort of word recognition got a lot better very quickly. But the sort of programming model, if you will, of how I code a sort of speech interface into a vehicle, we're still way behind. Yes, I can do, specific command recognition, but, back to Allison's example of, can the vehicle understand what I mean if I say, I'm feeling motion sick? No, today you would have to code that in as a specific path in the conversational system. So, we have just barely scratched the surface on how well our conversational systems can actually understand and interpret us and correlate or relate that back to what's happening in the environment, and then, what should I do about it as a computer system, right? Or what can I do about it? So that's an area where, we can do a lot better. We can certainly, use more AI, including deep learning models, and in fact, I'm really interested to follow up with you, Seton, to talk about the semantic models of the environment and the vehicle systems, so that the machine can relate spoken words to data that it's seeing, and then also translate its knowledge and awareness back into spoken phrases that the human can understand. So that's an area where we could do a lot better. We could do a lot more deep conversational systems that start to give the person a much more interesting interaction with the system, and also, hopefully over time starts to improve that trust factor that the AI that's in here is actually helping me understand what's going on. Not just with driving, but even with how the different vehicle systems are performing, or what maintenance might need to happen, and so on. So, yeah, I think that's a great space for sort of
That's a really good example.
interesting exploration.
Yeah, thank you. Guy?
Look, Michael. When it comes to artificial intelligence and what the performance and the capabilities will bring, we are still at the beginning of deploying this. And the reason I say this, I was waiting for the point that somebody brings up deep learning. So here it is. It's out in the open.
Let's do it.
Look, neural networks.
Which one of us are synthetic, right? Here we go. Yeah. No, go ahead.
Neural networks have been around for decades. It was a really hot item in the 90s. Everybody talked about it, and then became really quiet for a very long time until deep learning came around, and somebody found a different way to train the neural networks. Somebody found a different way how to build more complex neural networks, and boom, a couple years ago, and everybody is on the deep learning track. So what do we know what is still coming ahead of us in terms of the capabilities of machine learning in general? And here I said it, every time I say machine learning, I date myself, because machine learning has been around for a long time as well. So where I'm going with this is, what are we doing right now is really make decisions on a case-by-case basis. There's still a lot of power in rule-based systems. They're not all gone. Specifically, if you look at the example of computer vision in the automotive context, not every aspect of image classification has migrated to artificial intelligence yet, or is using deep learning. There's still a lot of life left in rule-based systems, and they will continue to exist for quite some time. Until who knows what further research will bring in the topic of machine learning, neural networks, artificial intelligence.
Yeah, I do want to second that, because I started in this field in the late 90s. And so, at that point we were coming off a lot of, Alvin and neural networks doing a lot of really interesting things. By the way, those neural networks drove 98% of the way from DC to California, right?
Yep.
So that's a pretty impressive demo from mid-90s technology. And then, I remember thinking at one point, neural networks are so old-fashioned, right?
Yeah, exactly.
So everything old becomes new again, right? Brian, you want to share your
I think I'll talk about some of the challenges that we face in, there's one thing to say have a problem and be able to show that you could solve it, but then actually solving it in production or putting it into a product. And that sometimes has been a frustratingly long and arduous journey. To go from the point where you can show that an AI system can do very well and solve the problem, but to get to the point where it's very robust and is built into a pipeline so that it's getting data, it's being monitored, it's being updated as appropriately, and then just automatically plumbed in and operating. That can be still very challenging today. I'll leave it at that.
Yeah. Chetan, I'm interested in your perspective on this too, as a startup founder, right? Part of this has to weigh doing demonstrations and showing capability versus preparing your roadmap for being able to do these kind of things. And the more I think about it, the more this does feel like a management challenge. So I don't know, maybe I'll tee that up.
It's a challenge of managing the expectations of different audiences. So you have to, yes.
How about this audience? Manage their expectations.
Yeah, exactly. Of course, the demonstrations are cool. It's nice to be able to look at something and see the light there, see the promise there. But then it is our job as startup founders, or anyone in the industry actually, to not drink our own Kool-Aid too soon, or to not detach from the reality and still see that, okay, so this seems to work, but can I get the 9 nines? It's like, oh, okay, I get 99.9% performance, but can I get the remaining 9s?
Can we make Phil happy?
As Phil, Phil is the king of 9s over there. Specifically to deep learning, it's actually not the problem of deep learning per se, but they suffer from that quite a bit these days. There are many open issues, but the most fundamental issue I see is that most deep learning models fundamentally overfit, which means that they are not generalizing properly. So these go hand in hand, and unfortunately, this is an open issue. Nobody knows any better than just getting subsampling a piece of the data from real world, which is much larger than however large data sets we can collect, and we try to make some mathematical sense, some inference on that data, and inevitably the data does not represent the world itself, and we've been constantly chasing that delta. I'm just stating the problem. I don't have any solutions to that. I sincerely hope that we get to solve that one day, but it doesn't mean that we should not look into interesting ways of interpreting the data. That's what the entire field is doing. And one of these days, maybe we'll first stumble upon a fundamental new way of interpreting the data, maybe find a couple of more brittleness issues with that, and then eventually get a full mathematical understanding of what's really going on behind the scenes. And that's maybe more of a statistics than machine learning or applied data science per se. But developments and product, the demonstrations and product development, they have to go hand in hand. You have to know the difference. You have to remind yourself that now you are looking at a demonstration, which is a sneak peek, hopefully the sneak peek of the future, but it's not here yet. And this is what we know how we can build today, how we can test against the well-defined specs today, and how we can comfortably delegate the task of, in my case, driving the 40-ton vehicle at 70 miles an hour.
Yeah.
That's a big responsibility. We just cannot be impressed by a little demonstration and carried away with that. That's.
I agree with the need to generalize and build generalizable models. And it's often tempting to build a model and then maybe you even overfit and it gets good results in common scenarios. And then what's even more tempting is to try to solve the problem by throwing more data at it, right? And thinking, well, I just need to find that additional scenario and get that data, and then I'll train the system, and it will be perfect. But as was referenced in the discussion earlier today about black swan events.
Yeah, that was great.
There will always be those rare events that are unanticipated, not seen before. And I think the real answer is we have to strive to build AI systems that have an even higher level of understanding, are generalizing, so that they can handle events that they haven't seen before, that they don't have the right data for. But
this is like the perfect tee-up.
This is
So the power of multi-policy decision making, which is the backbone of how we do behavioral planning, is the ability to generalize.
Yeah.
And so as a startup, we actually go and we talk with investors every time we have to do an investment round, which is an aggravating process, but also an enlightening process based on the questions that they ask you. And when they're asking us, like, well, how long does it take you to collect enough data to be able to operate in a new city? We're kind of scratching our heads like,
We don't.
We don't. So our first pilot that we did was here in Detroit. It took us a month. I'll be honest. Then we did a demonstration in Tampa, Florida. It took us 2 days. And we were able to put people in the vehicle after 2 days. Now we can do it within a day. Depending on the length of the map, we can do it within a day, but that's because the backbone of what we do is extensible and gets absolutely at that point that we can never think of all of the terrible things and weird things and crazy situations that are going to happen in a public sphere that is the road network. So creating systems that are adaptable is a much better use of resources. Our CEO is actually looking at Waymo's data, which is arguably very nice data because the road networks that they tend to test on aren't very challenging. But if they continue at the rate that they've been developing and the takeover rates that they have had in the past, Waymo, who many analysts will argue is way ahead in this race, has another 16 to 19 years, if you follow Moore's law, before their system is validated. And pair that against what we have been told, which is it's ready. It's done, it's out on the streets. And I actually remember back to when we were first fundraising, we launched the company in 2017. There was all this hype. GM had bought Cruise the year before. Ford had invested in Argo. And everybody was going to have these cars out. There were going to be thousands of cars out in 2018, 2019 for people to ride in. And when we were pitching, like, everyone is wrong, it didn't go over well. But it's been really interesting, especially even at CES this year, to watch the change in the dialogue. Like the fact that we're up here talking about explainable AI, I hope to everybody that you can understand, over the last 2 years, there's been a really big shift of reality setting in, which is good.
Yeah.
When we deal with reality, we can work towards products that can go out in the field. When we're just talking about, it worked once or it worked 5 times, and with the demo worked, that doesn't get us to scale.
I think it's been a huge problem with sort of what I call magic box syndrome in the last 2-3 years, where even executives in technology companies don't quite understand where the current capability limits are, and so we've really overpromised and been over-optimistic on that.
Well, just to second that a little bit before getting Jack, I think I was talking to SAE about this topic, right? And SAE is very interested in training engineers to be able to take these ideas into account. And when I was talking about it as a management problem, and what you just said, that really resonates with me. That it's not just like the new students that are coming in that need to understand how to do data mining and deep learning. It's like, hey, the bosses need to understand when they see something once, it doesn't mean it'll do it every time in every ODD in every context, which is also a great safety problem, right?
It is,
right, Jack?
It is, and I think, thanks, Mike, and I think this theme of managing expectations is really important. And we can think of it as an internal challenge, but I think it's just as equally an external challenge in terms of the people who use our products. I think there's some well-known examples of people becoming overconfident in the capabilities of the system, misabusing or misusing level 2 systems, for example, and pretending it's a level 4 system, right?
And that covers 4 of the questions we've gotten.
Yeah, exactly. So,
yeah.
And we did a study 3 years ago where we were trying to understand this trust relationship thing, and we brought them off the street, put them into an autonomous vehicle, and we were exploring some new kind of human and machine interaction things, and one of the models that we tried out was audible, and so the car would tell the user what the machine was doing. And so what happened was then the passengers wanted to talk back and ask questions and tell it to stop or turn. They'd say, turn over there. Like they're pointing, like the machine, so their mind already flipped a bit that, oh, it's talking to me, so now I expect I can talk back and it's going to understand me, right? And that was something that we hadn't considered. And so I think people's perception of these machines and what they are, and are they soulless or not, I think changes often their perceptions on the quality or worth of the machine. I'll share one last quick example, just because Mike knows the story, but there's a fascinating research study that Professor Nicholas Epley did from the University of Chicago. And he took people off the street and put them into 2 autonomous vehicles. And they were identical in every way in a simulated environment. They are identical in every way, same route, same vehicle, same interior, same sensors, same everything, including a forced crash that happened from some other car that crashed into the car that the subjects were in. The only difference between the 2 cars was one was anthropomorphized, meaning it had a name, it had a gender, and it had a voice, and the other one was not. Afterwards, when they talked to the passengers about, hey, what did you think about the experience? The people that were in the plain, soulless automated vehicles blamed the automated vehicle for the crash. The people that were in the anthropomorphized vehicle blamed the other car. But they are identical in every way. So their managing expectations, if you will, of the technology and building that relationship can change entirely our customers' perceptions of the systems and what they're doing and why, and should I trust it or not, and do I blame it or not for an accident even?
Yeah. Well, since you mentioned blame and since you mentioned accidents, I guess we can wrap up talking a little bit about liability and risks and safety. And again, I think that we can learn a lot, especially in a public discourse, talking about what some of the failure modes and problems are of early kinds of AI. Even why spam filters don't work and things like that. Those might be really useful lessons for us to figure out how we go about putting together safety cases to argue for the correctness of our technology. We're certainly working a lot on that with our underwriters laboratory standard that we're trying to develop. Maybe we can pull some other ideas from some of the engineering side of things as well, because there always needs to be some kind of assurance case, because ultimately you're using the automation to try to build a design faster, and the human gets a little bit out of the loop there. So maybe we can start down here and talk a little bit about some strategies that you've seen put in place to try to handle some of these thorny issues of liability and of safety.
Well, yeah, I think we're just starting, so it's not even early days, it's ground zero for, starting to think about liability and trust in AI systems. And that is a conversation that absolutely needs to happen, and it needs to be very pervasive. So if you look at our engineering processes in automotive or any other industry, frankly, we've just barely caught up to where, software is a sort of primary thing in the engineering process, and we have now, essentially process standards for how you incorporate software into system engineering. We haven't got that for AI at all yet. Our engineering discipline just treats AI as yet another bit of software, but I believe it's fundamentally different, and we have to evolve that process to deal with things like, what's your trust in the data? What were your data sources? What's the, what are you doing to mitigate bias? There's all kinds of things in the AI, let alone the sort of safety critical aspects, but the fact that these are, learning algorithms and they are based on data, not human coded, that is so fundamentally different that we have to evolve our system engineering methods to take that into account, and that's something I'm personally, working on, and open invitation if anybody else is sort of interested in that conversation. I'm all over that, but it's really ground zero. We haven't done anything yet as an industry to really accommodate that.
It's a good call to action.
Yeah.
Kai?
That's a good point, and maybe to add what Skye was mentioning, it's really interesting because artificial intelligence has been around much longer than the automated vehicle discussion for many, many years, and nobody, really initiated a large, ethical or legal or regulatory or legislative discussion. We're talking about humanoid robots or factory automation robots.
Yeah.
Maybe a little bit, depending on the particular example, but not to the magnitude we see it then. And then, what was it, 2010, 2011, it became public that Google at the time was working on the AV, and then we've been talking about liability topics, legislative frameworks, or the lack thereof, regulatory frameworks, or the lack thereof ever since.
Yep.
And we still haven't solved it, to Skye's point. I think, I think we have done some things, I want to say. It's not like we haven't done anything. But, what for me the clear conclusion is, this is not for one individual player in this space to solve. No way. This really requires an interdisciplinary discourse on the topic, including legislation, including regulation, including academics, including industry on the topic, because it goes right back to the title of this very panel. What is the benchmark for AI? And I mentioned before, we're trying to simulate human behavior. Is that a good benchmark? I would argue 1.3 million deaths worldwide every year, around close to 40,000 alone in this country every year, which means more than 100 people are killed by a traffic crash every day.
Yeah.
More than 100 people every day in this country alone. Is that a good benchmark? And what if we cut this in half? Is this a good number? Is this a good enough number? Or do we have an even more intense dialogue about the 50% that still do happen versus the ones that we avoided, bringing new technology and innovations in this space? So there is at the moment no product liability protection. There is no legislative or regulatory protection in this topic. I think we have to be very, very careful with a step-by-step approach when we launch these systems. And maybe one last thing I want to add is there's a big difference in deploying artificial intelligence in an automotive context, because there's on one hand the training task and the continuous training task once you're running in the vehicle versus the real-time operational task. And we need to separate those two when we talk about deployment of AI in the automotive context.
That's an excellent point. Brian?
Boy, my better judgment tells me when you're asking about liability that I'm out. But,
That's fair.
That's fair. So more seriously, I think it's obviously an important topic because AI has such tremendous potential to improve people's lives in the world. And so I think it's incumbent upon us to try to achieve that. But at the same time, it could obviously be misused, either intentionally or even just recklessly. And so I think the key to avoiding those situations is just transparency and allowing people to see everything that we're doing to avoid bias, to test the systems, and test them again and again and again in the AV world. And just, again, transparency all along the way.
Yeah. That's an excellent point, yeah. Chetan?
Similar. I think the key going forward is going to be painful. So that's the pessimist part of it. So I think the entire insurance industry, especially, is looking into that, and they are trying to transform themselves. They are trying to reinvent themselves, and it's going slow because that's an old school industry. They have a certain way of doing things, etc. But we will get past that inevitably. And when we get past that, the way the automation or autonomous vehicles or AI is going to function in the future is going to bring a whole lot more transparency in the actual mechanics of how a system is working and what exactly happened. So one of the biggest issues in liability is to do credit assignment properly.
Yeah.
And doing proper credit assignment requires proper scenario reconstruction, or going back and checking exactly what happened and whose fault was that. So it's often argued that it's really hard to, if there's no driver or if there's no human around, how are you going to associate liability with? But if we have data, and if we can actually do this deconstruction and look into the right ways, we can really account the right parts of a particular system or right AI subsystems as accountable or as responsible for a certain outcome. It's maybe too in the future, but I think that's what we are on path for.
And that's the optimistic part.
That's the optimistic part.
Yeah.
It's going to take long. That's the pessimistic part.
So I've stated before, AI for us needs to earn its seat at the table, so we really don't use it in our real-time systems. That said, we have had to figure out how to work with existing industries. We're out on the roads today, and part of that is we've had to work with insurers to find someone that can underwrite our system, and we have a really transparent dialogue with them. They come to our offices and do whole half-day offsites to understand how does the system work, how do we train up the people who are doing the maintenance, all of that, and it's a collaborative relationship. And what's great is that as slow-moving as the insurance industry is, they know that they need to change.
Yeah.
And so for us, it's been great to find partners in our underwriters that want to have that dialogue. And the same thing with our partners. We're working directly with cities that want to write the playbook of how do you think about bringing self-driving systems into your transportation ecosystem. And it's huge, especially for insurance companies and policymakers. They can't go create the future until they're able to touch it and feel it.
Yep.
And we're creating those opportunities now, and we think that that's really important because at the end of the day, to be successful, we need passengers, but we also need partners. Unless people are self-insuring, you still need an insurance company that wants to balance your funds and things like that. So there's a role for insurance to play, and we need to just have that transparency. And I think it's actually a really exciting time to me when you're constraining the operations appropriately. There's a lot of willing partners.
Yeah, I agree.
Yeah, I think transparency is key. I think I'll second Skye's comment as well around system design. Avoiding liability and risk for being at fault for an accident starts with design, and a design that is safe by design, whether you can use formal methods or not, or you're just providing lots of documentation for other eyes to look at, so you can have independent assessment and common metrics, so that we can have sort of an apples to apples comparison of what people are building. It's hard to know something failed if you don't have a definition of what it should have done otherwise, so it kind of all goes together.
Yeah, I agree. Well, I'm afraid we're out of time for the trolley problem question.
Oh, darn.
Unless
I'm
anyone
waiting
wants.
for that.
Unless anyone wants to wade into that one. Any parting comments from the crowd here? I really appreciate the time and effort going into this and your thoughts here. I think this has been remarkably useful, and I appreciate the questions from the audience as well. Definitely thank you for coming out and watching us. But thank you very much.